Good afternoon. Today we will start with chapter 5. Vectors are talking about two-dimensional motions. In the chapter 4, we talked about one-dimensional motion. It could be horizontal and vertical. Today, in this chapter, we talked about projectile motion. These projectile motions, they are later on we'll talk about their components, but first let's talk about the vectors and scalar. Now, the quantities are vectors and scalars. Any quantity, it could be vector and scalar. A vector, it's a quantity with a magnitude and direction. It's need magnitude and it's need direction. Some examples of vectors like the displacements, the velocity, the acceleration, the force, all of them. If I talk about velocity, or I want to describe the velocity or the acceleration, I need the magnitude, like 5 meters per second square, 5 Newton, and the direction, to the north, to the east, to the west, and so on. For the scalar, it's a quantity also, but need only magnitude, like the time. It's take with me 5 seconds. It's enough. I didn't need to say 5 seconds to the right, or the volume of the cone is 5 meters cubic to the left. Doesn't need. If I want to describe the volume, I need only the magnitude only. These are vectors, the scalar and vector quantity. Now, vectors are, now by the way, can the vectors have a negative sign?
Yeah, if they are in the opposite direction to what I'm speaking about, right?
Yeah, but here the magnitude, it's only this negative sign. It means that it has a negative direction, but it doesn't have a negative magnitude. If you say negative 15, that means the magnitude of the vector is positive, but this negative sign, that means is the negative direction. What about the scalar? Can it be a negative sign?
No, because it isn't direction.
Yes, I cannot say that the mass of the book is negative 5 kilograms, or the distance from this computer to this board is
of them can have negative.
Centimeter. Sorry?
So both of them can have negative?
Yes, can't have negative. But if you see the vector has a negative sign, that means it's for its direction. It's go with a negative direction. Now, how can we represent the vectors? The scalar just with a number, 5, 4 with a unit. What about the vector? To represent the vector, I need an arrows. All of us know that each arrow, it's need head, it's need a head and a tail. This is an arrow. This arrow means I represent, or by using this arrow, I will represent the vector. Like this one is a 3 meters per second. This is a vector of a velocity. That means my magnitude is a 3 to the right. And so if you see it like this, it means it is 8 meters per second to the left. This is a way how to represent the vectors. Now, as we said in chapter 2, the vectors are like a number. It can be added, can be multiplied, and it can be subtracted. How it's be added? It's how it's added. What's the meaning of two forces are added, or two velocities are added? Look at.
Can you use the parallelogram?
Sorry?
The parallelogram law to add them.
Yes. So it's like two arrows, it could be parallel to each other. What does it mean? Like if you have this box as an example, and for this box, you know that there's two forces acting on this box. Now look at these two forces, F1 and F2. These two forces with the same direction.
So they will be added.
Of the tails have, or the head the same, and the tails are in the same direction. So both of these two arrows are in the same direction. So the F resultant will be F1 plus F2. It will be added because they are in the same direction.
Actually, we took this.
Yeah, in chapter 2, I think, yeah. Now, this will be added. How the resultant will be? Here now, as I told you, the resultant, if it can be represented, it likes this. The head of the first one, oh, this is the vector of the first one. If it's added, that means I will connect the tail of the first force with the head of the second force. That means they are with the same direction, so the resultant will be added.
Both of them are in the same direction and they will take all the forces.
Yes, I will say like 5, 10, you will say it is 15 Newton, and this is the direction of it.
Maybe to the left, yeah.
If they are in the opposite, one to the left and one to the right, or one upward and one downward, like this one here.
We are going
this
to
is F1, and there's there's a box as an example, and there's an F2 acts on it down. So what we have to do now? Here now, since F1 is upward and F2 is downward, and I want to write the resultant, I represent it like this. I will draw F1 with a head down and tail up, and since they are in the opposite direction, so I will draw the head of the first one with the head of the first force. It will be like this. These two resultants here, as you see, it means they have to be subtracted. One to the left and one to the right, or one upward and one downward. They are on the both in the opposite direction, as you see from here. That means the resultant here, the F resultant, will be subtracted. F1 minus F2, or F2 minus F1 according to the magnitude. And the answer, it will be, as an example, if here is 10, if here is 5, you will say 10 minus 5, which is 5 Newton,
which is 5
upward. Okay, this is if they have added or subtracted. Now this is for the forces, but here our lesson or our chapter is not talking about forces, it's talking about velocities or acceleration. They are the same. Here, if we have this resultant force with V1, and there's another one that's parallel to it, which is V2. They are parallel, they are the same direction. So I want to represent it. I will say the resultant will be like this. This is for the V1. I will add them. That's mean I will pick. The problem here, that's with, wait please. This is for the resultant one. And this is for the resultant 2. They are with the same direction. I want now they are with the same direction, so I will add them. What's the meaning of add them? I will pick this one and I will add the tail of the second arrow with the head of the first one. By now, as you see, they are added. They are in the same direction. So if this is 7, wait. So if this is 7 and this is 8, it will be added. It will be 15 Newton. I will draw the arrow like this and say it is 15 Newton. If here, both of the arrows with the same direction. Now, how it will be? But now with opposite direction, like this now. Now they are in the opposite direction. What does it mean? I have now to find the resultant of them. So I will pick this one and I will put the tail of the first with the tail the head of the first with the head of the second.
Which means the opposite.
This means they are opposite and they are in the opposite. So the resultant will be subtracted. So if this is the pink is 5 and the brown is 8, I will say it's a 3 Newton to the left. Why to the left? Because if here is 8 and here is a 3, and since 8 is greater than 3, so we'll say it is 8 minus 3 equal 5 Newton as an example to the left. What does it mean? That means if you have this box and as an example, Rose act with it with 5 Newton and Habiba act with the second direction with 2 Newton. Okay, so this box, where it will go? Imagine that there's a box, one of you push it with 5 Newton and Habiba push it in the second direction with 2 Newton. So the box will go to the left or to the right?
To the left. We'll go 3 Newton to the left.
Yeah, it will go 3 Newton to the left. Why to the left? Because Rose acts with it to the left with a force that's greater than the 2 Newton or greater than Habiba, so the box will move to the left. But if both of them are acting on this box with the same direction, it will go to the right with the summation that's added by them, which is 7. So it will go to the right now with 7 Newton. So these two vectors, it can be parallel and sometimes it could be perpendicular. Let's see now the perpendicular one. So if they are parallel, the magnitude of it is very easy. I just add them or subtract them. And the direction is going to be according to the highest magnitude. If it is perpendicular, we will see now what we have to do. Now, vectors components. Because a vector has both magnitude and direction, you can separate it into horizontal and vertical components. That means if it has, if they are perpendicular, one to the left and one to the right, like this. 1 of the forces to the left and one of the forces to the right. Okay, I want you now to add or to find the resultant of them. To find the resultant of them, here, let's say that they are perpendicular. On the same box, one of you push it to the right and one of you push it upward, where the box gonna be moved to. Here we say that it has a x component, and it's behind fx, and here we have f on the y-axis. That's we say fy and fx. How can we write now, or how can we find its resultant? The first step, you will continue them like this, like parallelogram. Then the resultant will be a diagonal coming from this point ending with this one. This will be now the resultant. It's a diagonal in this rectangle. So this is the resultant, and we know that each resultant, it's need, since it's a vector, I need to find the magnitude, and I need to find the direction. To find the magnitude, look at this here. It comes like a right triangle. So to find the resultant, I will use the Pythagorean theorem. We said in it that R, it will be the components of f of x squared.
Did you say the Pythagorean theorem?
Yes.
Now we have geometry.
The square root. So Mara, I told you the physics, it's like math. So the resultant here, it will be the square root of, here, why we say this, it is this hypotenuse. Wait, I want to change the color. I want this hypotenuse. This hypotenuse is f of x squared plus f of y squared. Since this I draw another line segment that's parallel to fy, so it will be also fy. So the hypotenuse, it will be fx squared plus fy squared. This is a resultant. After that, I will find now the magnitude of the resultant in Newton or in meter per second. It's the Pythagorean theorem. The Pythagorean theorem, we say the hypotenuse squared is the first leg squared plus the second leg squared.
Yeah,
and
but
to
we
cancel
didn't
it.
Oh, after that, yeah, okay.
Oh, this is the resultant. Now I need to find the direction. What's the meaning of direction? Direction that since now this resultant is moving, starting from f of x, where it's move? Does it move to this direction or to this direction or to this direction? Where it has to be? I will find the direction of it. Here, if it is perpendicular, the direction will be using the trigonometric functions, sine or cosine or tan. For this case, you will use tan because here is the direction I mean. I need now to find the angle that from where this resultant R is located up farther than f of x. So I need to find the angle. To find the angle, I have f of y and I have f of x. Only these two magnitudes I have. So I will say an angle theta is tan inverse of f of y over f of x, the opposite over adjacent. So if they are perpendicular, to find the magnitude, I will use r equal fx squared plus fy over the square root of the first horizontal exponent squared plus the second horizontal squared, and the theta is tan inverse of the y exponents over the x exponents. By now, we find the resultant R with its direction. This is if it's perpendicular. If it is parallel, I will add them or subtract them. This is the way how to find the magnitude. And to find the direction, I told you according to the highest or to the greatest magnitude of the components. So now, because a vector has both magnitude and direction, you can separate it into horizontal x or vertical y components. To draw this, draw a rectangle with a horizontal and a vertical sides and a diagonal equal to the vectors, as I did before. This is the Vx.
So teacher, only in this case, right? Like we will use the trigonometry and like this when we have a direction that is up and the direction that is in
they are perpendicular. Yes, only for this case. So if you have f of x and f of y, they are perpendicular, you will draw a rectangle to continue it. Then you will draw a diagonal connects between these two vertices. This diagonal will be the resultant force. Now, draw arrow heads to one horizontal and one vertical side to make the original vectors. Okay, after you draw the components, you find their length by using the simple trigonometry. There's appendix, I don't know what to talk about them. Let's have some examples now here. Every March, the swallows return, or before I solve the examples, is there anything that's not clear?
No, thank you.
No, teacher, everything is clear.
But wait, teacher, can you repeat why you wrote -1? Tan -1.
Okay. How, wait. Now, in math, if we have to find the angle theta, you will say tan theta. It is opposite over adjacent. This is the tan of theta. So tan, this angle here, theta, is f of y, which is opposite, over the adjacent, which is f of x. Is it right? This is how can we find the tan of theta. Now, what can I do if theta is known? Like, if theta is unknown now. This way, if I know f of y, now, why I use the tan sometimes? Because if I have the angle as like this, if tan 40, and I told you that up is 5 and down is x, you can find f of x by this way. If you know that 5 if y and f of x is 4, and I want you now to find tan, the angle. How can you find the angle? Shall I try to say 5 over 4, the tan of it? Let's try 30. Then let's try 60. Then no, I will not put all the possible angles to me, and then I will find them. You can use the tables if you want. The table tell me that which one is 1.125, so the angle will be approximately something. Or you can say use the calculator. In this calculator, what can I do? I will say theta, it will be tan inverse of 5 over 4. If I put tan here, I will write it as tan inverse. So it will be tan inverse of 5 over 4. On calculator now, if you want to find it, you will say shift tan. Okay, shift, then tan. Then I will write 5 over 4, and the angle it will be 51.3.
Okay, thank you a lot, teacher.
All right. Let's have now these examples here. Every March, The swallows returned to San Juan Capistrano, California after the winter in the south. If the swallows fly due north and no, if it's fly to the north and cover 200 kilometers to the north, to the north with 200 kilometers on the first day. On the second day, 300 kilometers with the same direction. And the third way, 250 kilometers on the third day. Draw a vector diagram. So they are both of the third, on the 3 days, they are the same direction. 200, 300, and 250. They are on the same direction. So I will add them as you see from here. They draw them with the same direction. So since they are with the same direction, I will add the magnitude of them. Because the swallows continue to fly in the same direction throughout the entire trip, these vectors simply add together. This can be shown by placing the displacement vectors head to tails. As I told you, here you have these two vectors. Give me a minute, please. Here we have this vector. This is for the first day. And there's another one for the second day. And there's another one for the third day. After that, they add them. The tail of the third case here. So they are in the same direction. I will add them. I will say 750. And what's the direction will be? To the north or to the south?
North.
North.
To the north, because they add all of them and all of them to the north. So it will be 750 kilometers north. By this way, I find the magnitude, which is 700 kilometers, and the direction, which is to the north. Let's do now second example. In this one here, in August 7, 2007, let's take the important one. Various bonds of the San Francisco Giants passed Hank Aaron to become Major League Baseball career home run leader by hitting his 756th home run. If Ponce hits the baseball due west with a speed of 50. So the Ponce hit the baseball due to the west with a speed of 50 meters per second. So the first step now, what I have to do, I will draw the vector here. It was to the west 50 meters per second. So let's draw now the arrow like this with its magnitude, which is 50. And the ball encounters a wind that blows it north at 5 meters per second. So, what is the resultant velocity of the baseball? So, the bond hit the baseball. So here is the bond. He hit the baseball here. Then the baseball, it goes with a wind. It goes upward. It comes like this then. So the bond hit the baseball and the wind acting on the baseball, it's gone up. Find the resultant now. Now, as you see, here they are two vectors. They are perpendicular on each other. The first one goes to the west, and the second one, it goes upward or to the north. So where the resultant will be?
We can use the Pythagorean theorem.
Yeah. Here now we have a 5. Here we have a 50, I need now to draw the resultant force that comes from this one heading to this one. Since it is perpendicular, as I told you before, you have to find the resultant and the magnitude. The resultant by the Pythagorean theorem and the magnitude by the tan of theta. Now, so to find now the resultant force, our resultant, VR, I will say it is the square root of the exponents on the x-axis squared plus the exponent on the y-axis squared, which is 50 squared plus 5 squared. 50 squared, 2,500 plus 25. So VR will be the square root of 2,525. The square root of it will be 50.24. This is now the magnitude of the resultant velocity. So the baseball will goes with 50.24 meter per second. Now where's the direction? I will do the same. I will say theta will be tan inverse of Vy over Vx. Vy over Vx. So tan inverse of 5 over 50. So tan inverse of 5 over 50, which is theta will be 5.7. So it goes with the direction of 5.7 degrees. This is now, by now we find the resultant force and the direction of the resultant force. Is it clear?
Yes,
Yes.
teacher.
Yes, it is.
Yes, teacher, it is.